All right, so we are starting module 4. Unfortunately, we have to cover material while you guys have a midterm this week, or had, depending on when you watch this. And unfortunately, this is like the beginning of some pretty tough stuff, but we'll hang in there together, and hopefully in lab we can help clear up a lot of this stuff. And yeah, so normally I had been sectioning off my lectures based off of chapter. We're still covering 3 chapters today, although I think it makes more sense. So here's the 3 chapters. I think it makes more sense for me to break my lecture a little differently, where I do an intro to organic chemistry, properties and naming, and then reactions. So this is video 1, and we were just going to be talking about what is organic chemistry, how the heck do we begin with organic problems. So organic chemistry started in the 18th, 19th century, where organic was a term used for compounds extracted from plants and animals. So organic stands for organized systems. So the food industry kind of stole this term and used organic for food grown with or without pesticides or synthetic fertilizers. But really, when we talk about organic chemistry, we're not referring to food grown with or without organic pesticides, or I'm sorry, yeah, with pesticides. We're talking about chemistry that is centered around carbon. So carbon is a very important backbone to all of these molecules. They contain a lot of carbon atoms. So why are all these molecules centered around carbon? So carbon is a great backbone for larger molecules because it has 4 valence electrons, and therefore it can make up 4 bonds with other atoms. And so here I have some classic depictions of organic chemistry molecules where we have a long carbon backbone chain here, right? And it's depicting, okay, so if I have a carbon-carbon bond here, I can have 3 more things attach off of this terminal carbon. The middle carbons, they're each attached to their own other carbon on each side, so they can have 2 other things attached. And down here I have examples where here this carbon is connected to another carbon in the chain, as well as an oxygen, and then a hydrogen is filling in those remaining carbon or bonds. So part of the challenge with organic chemistry is that they depict models very differently. So we can have molecular formula, which is what we've been dealing with in class so far, but now we're building to bigger molecules where, you know, we can have the structure matters. So we can depict this structurally. So I have 3 carbons in the backbone here. Come on. Right, and then I have 8 hydrogens. Right. And I could go on and so forth. Those are some crazy molecules. I forgot to edit this slide, but right. There's also condensed formula, where basically you write out the carbon and whatever's attached to it. So each of these carbons start off the condensed formula. So this first carbon is CH3, where the second carbon is CH2, and the third carbon is again CH3. So that's a condensed formula. And then there's even stick models. So stick models are where a point represents a carbon, or the end of a line represents a carbon. There's a lag in when I write it on my iPad and then when I actually see it. So it's kind of, sometimes I'm writing over myself there and I don't notice it. All right. And then the hydrogens are implied in the stick model. So if I was doing this same molecule here, C3H8, I would have 3 points, right? So here's 1, 2, 3. And then all my other hydrogens are implied. So it's implied that this is a terminal carbon and therefore it would have 3 hydrogens attached to it. It is implied that this is a middle carbon and so that would have 2 hydrogens attached to it. And again, a terminal carbon, it's implied that the hydrogens are attached. If we throw in heteroatoms, such as in this example here, heteroatoms are any atom other than carbon and hydrogen, and they get explicitly written out. So C4H10O would do 4 carbons. So 1, 2, 3, 4. And then I would have one other bond coming here to an oxygen. And then it would be implied that there'd be 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, 3 hydrogens here. And I'm assuming there's probably, let's see, what is our count at? 2, 4, 6, 8, 9. So there's probably hydrogen hanging out here. Okay. So we're going to see a lot of these guys. So I wanted you guys to understand where those come from. We'll even see 3D models in OWL, but you will not see 3D models on the test. So I don't include a lot of 3D models on my lecture slides because you only really see them on OWL. So here's another slide showing how to, and it kind of shows you these 3D models, how to depict, different chains here. So something else about organic molecules is that they can form rings, and we'll get to that a little bit later. So this structure here is a cyclo alkane ring, which we'll talk about all that. But so I just wanted to show you that slide. So there's some examples. Down here, we're even depicting a double bond, right? So there's 2 bonds between the carbons and a triple bond. And we will talk about those in naming in video 2. So these are probably not updated. These numbers probably don't correspond because I just pulled up my old slide set from last semester. But one of your OWL questions should look similar to this, where you're matching the molecular formula with a structural formula. So here we have well, I guess, I'm sorry, this isn't the molecular formula, this is the condensed formula. So here we have, let's see, 4 carbons with 2 oxygens in between that 3rd and 4th carbon. So I see that as this molecule here. So here's my 1, 2, 3 with 2 oxygens connected to that, between that 3rd and 4th carbon. All right, so this next one here is 1, 2 with an oxygen and a nitrogen between, and then 3. So I see that one as there. So I have 1, 2, here's my oxygen and nitrogen between, and then 3. Here we just have 1 carbon and then a nitrogen group. So this guy. Here we have 2 carbons with the last one being an oxygen. And then here, kind of similar to the first one, we have 4 carbons, but this time the double oxygen is on the terminal end. And so I see that as that one up there. All right. So you'll get some good practice there. So the same question might generate the 3D structures. And so in the 3D structures, white are hydrogens, blues are carbon, and red is oxygen. So here we have a carbon with an oxygen smashed in the middle, and I see this guy. So here's the carbon, oxygen smashed in the middle. This one here, we have 1 carbon, but an oxygen on top and to the side. I see that as this one here. So here's our carbon, oxygen on the top and to the side. Here we have an all carbon structure. So I see that down here, there's 4 carbons. All right, and then here's 4 carbons with a center oxygen. So carbon, carbon, oxygen, carbon, carbon. All right. Okay, so I kind of alluded to this, right? But rings, carbon can form rings. And sometimes this is more energetically favorable over a carbon structure in a line. So the same rule applies where each point is a carbon. So here, this is a 3 carbon structure, 1, 2, 3. Here's a 4 carbon, 1, 2, 3, 4, 5, and 6. This is most common, but it's you'll see a lot of OWL generates a lot of examples with all different kinds of numbered rings. But in our body and stuff, a 6-membered ring is the most common. All right. So this brings us to functional groups. So right now we've talked a lot about carbon and hydrogens being the basis of organic chemistry, but there are some common groups that hang off of these carbon chains. So for example, here's our carbon chain, and here's a popular group that hangs off hydrogen or carbon chains. And so this is an OH group, also known as an alcohol. And so on the next slide, I have the functional groups. So these functional groups, these are groups that you're going to want to know in and out, and I'm going to erase some of them that you don't need to know here. So you don't really need to know ethers, alkyl halide, thiol, or esters. We're going to skip those, but I am going to add one more here. It's isopropanol. So here we have it's CH3, CH3, and then a CH3 down here. So this is isopropanol. All right, so these functional groups. So this line here just depicts the rest of the structure. Sometimes this is written as R and then say CH3, right? So it's just showing us, hey, it's this group attached to any carbon chain. So these functional groups are like the basis of organic chemistry. And so while I might not spend a whole lot of time on this slide right now, I would highly recommend that you spend a lot of time familiarizing yourself with what these functional groups look like, whether that be flashcards or some kind of Quizlet, drawing them over and over. It will be really beneficial for you to know these in and out, okay? So this organic chemistry lecture is broken up into 2 weeks. So we cover these functional groups, but they're split into 2 weeks. So the first week, we're going to talk about alkanes, alkenes, alkynes, and then we will also talk about alcohols. Okay. And then next week we will talk about aldehydes, ketones, carboxylic acids, amides, and amines. We have a lot next week. All right. So your AL question 1, and I am confident that this is the same number, has you do this matching again, but matching now structures with the functional group present. So again, you're going to want to familiarize yourself with that slide before you try to tackle this, but I got these ingrained in my brain. So a carbon double bonded to an oxygen sandwiched between 2 other carbons is a ketone. A carbon double bonded to an oxygen, but on a terminal carbon, is an aldehyde. So aldehydes and ketones are both carbons double bonded to an oxygen. It's just where they're placed in the carbon chain, okay? A nitrogen present in any part of the structure is an amine, right? So just nitrogen anywhere. Oof. All right, so I preluded this one a little bit a few slides ago. An OH group anywhere in the chain is an alcohol. And similar, but slightly different, a carbon that is double bonded to an OH group and a double bonded oxygen is a carboxylic acid. So this one's a little tricky because it's kind of a mix between a aldehyde and an alcohol, but when they're placed on the same carbon, it's a carboxylic acid. Okay. So we're going to hear this term hydrocarbons in organic chemistry. And so hydrocarbons are just regions of carbon chains that have hydrogens coming off of them, right? So it's solely carbon and hydrogens together. And so we can have saturated hydrocarbons and non-saturated hydrocarbons. And so saturated means it can have the maximum amount of hydrogens. It's saturated with hydrogens. Right? And so basically you have to have all single bonds for this. unsaturated, I've never heard it called non-saturated. I think that's a typo on my end. Unsaturated is when carbon is not maximizing its amount of hydrogens. And so instead of having four bond, or I'm sorry, it still has 4 bonds, but it's not necessarily connected to 4 different atoms. That is when it's unsaturated. So it's not maximizing its amount of hydrogens. Right? And so this happens when you have double bonds or larger. So double or triple bonds, basically. Okay. And so why I bring that up, we're not going to talk about it too much, but it's important in the 6th and 7th module, in which we talk about biochemistry and how we metabolize the saturated and unsaturated bonds. Okay, so same picture, but now we're going to focus on something a little different. So we're going to start with our first 3 functional groups here. Okay, so we have alkanes, which are all single bonds of hydrogen and carbon. We have alkenes, which is where a double bond is present, but again, all hydrogens and carbons. We have alkynes, which is when there is a triple bond present. Oops, I can't spell triple. But again, all carbons and hydrogens. And then we have aromatics, which are those rings. We're not going to stress too much about that right this second. Okay. So I love this little, I guess this is a meme, a very old school meme. This is something I found when I took organic chemistry eons ago, but I thought it was funny. So it's porcupine, and it has all single bond coming off of it. Porcupine, and it has double bonds coming off of it. And porcupine, and it has triple bonds coming off of it. That will make sense here in a second. So alkane, right, is all the single bonds. It has the ending ane. Alkenes have double bonds, right? The ending ene. And alkynes have the ending ine for triple bonds. And we'll reiterate that in the second video, but that's why this meme is kind of funny. All right. So your OWL question 2, and again, I can't promise that these numbers align, but it asks you to classify the hydrocarbons as alkane, alkene, alkyne, or arene. This is just if it has a ring. Okay, so this first one has a triple bond, and so it's an alkyne. This one is I think the drop-down menu says arene. This is a it's got a ring, so it's an aromatic. This has all single bonds, so it's an alkane. And here we have a double bond, so this is alkene. Okay. All right, so that concludes our video 1, Introduction to Organic Chemistry.